Hi, welcome back to my channel. This video will be part 4 of Working Stress Design Principle. Still under course outcome 1, Working Stress Design Principle. In here, we will be having the criteria and guidelines for the design. To start, criteria and guidelines. From NSCP 2015, under section 429.4.1, flexure in concrete shall not exceed FC less than or equal to 0.45 FC prime. We recall that FC is taken to be the compressive stress in your concrete. So from NSCP under WSD, the criteria should be not greater than 0.45 FC prime. From NSCP also, under section 429.4.2, tensile stress in reinforcement, which is FS, denoted as FS, shall not exceed the following. If we're using grade 280, it should not be greater than 140 megapascals. If it's grade 420, it should not be greater than 170 megapascals. Recall, FS is the tensile stress in reinforcement or steel. From NSCP 2015, section 429.6.4, tensile stress in reinforcement FS shall not exceed the following. Oh, I'm sorry. It's just a repetition of the other one. I think this should be tagged as the modular ratio. Sample computation for the modular ratio. ES over EC. ES would be 200,000 megapascals. And EC for normal weight concrete would be 4,700 lambda multiplied by FC prime. But in here, lambda has been taken to be 1.0. In case there will be other values, you can apply your knowledge on a different value for EC. But first, let's review that N should be rounded to the nearest full number, but should not be less than 6.0. ES, again, 200,000 megapascal. And for other values of EC, it could also be computed as WC 1.5 raised to 1.5 multiplied by 0.043 times lambda, the square root of FC prime, taken from section 419.2.2.1.a. In case it is having a WC between 1440 and 2560. Lambda could be 1, or it could be 0.75, or it could be a different modification factor. Please check section 419 for the other parameters that could be used in determining your lambda. But again, unless specified, your lambda is assumed to be 1. In designing under balance condition, what we do is FC is equal to 0.45 FC prime, and FS should be either 140 or 170. So we set these conditions in designing your balance condition. So in the future, there will be three types of design. One is balance, number 2 is over reinforced, and number 3 is under reinforced. But mostly, the one that we recommend really in the application in actual construction would be your balance condition or your under reinforced condition. So going back, what is balance condition? This balance condition could be summarized in which the yielding of your concrete and of your steel happens at the same time. So they will reach their maximum strains in bending, both for tension and compression at the same time, because we're setting it as a balance condition, which is a good thing. I think for me, it's a good thing because the understanding and the analysis would be, it would both reach its maximum potential. Therefore, we can maximize their, not maximize, but actually can understand their simultaneous reaching of their capacities. For concrete, it's tension, it's compression, and for steel, it is tension. So for balance condition, we use different values for k and j. So if you remember, your k could be the square root of 2n rho plus n rho minus quantity squared minus n rho, and your j is equal to 1 minus k over 3. But in here, the balance condition would be quite different. If we take a look in this stress diagram and then we label k to be balanced, so kb is here labeled kb, and then j would be your jb. Again, k and j are your investigation factors in which the ratio and proportion could be applied. This could be, let me draw this one and indicate that we're taking the ratio and proportion on this triangle. Alright, on this triangle. Okay. So for in solving your KB would be expressed in this equation. So KB, D is here. That's the height of the small triangle. And then the base would be FC as taken here, equal to, again, the larger height would be equal to effective depth D. And then your height or your base would be here, the summation or the sum of FC and Fs over N. That's why it turned out like this. So simplifying the equation or the terms, we can now solve for KB equal to 1 over 1 plus Fs over NFC. Again, Fs is your tensile stress for your steel. And then here, Fc is your compressive stress in your concrete. K is the transition factor under balanced condition. For J, it's similar, 1 minus K over 3, but we label it or we indicate that the K value would be under K balance. So this would be used, this values Fc, Fs equal to 0.45 Fc prime and 140 or 170 respectively under balanced condition, and making sure that we're using KB and JB as your investigation factors. To continue, this is a sample problem. We'll try to apply our knowledge in or understanding in singly reinforced rectangular beam using flexural equation and applying the knowledge of our design and criteria. We calculate the moment capacity of the beam in problem 1 using SRRB Flexural Equation, using Fc prime equal to 21 and Fs equal to 170 megapascal. Use working stress design principle. So this is the value in problem 1. If you can remember, applied moment is 70 kilonewton meter, Fc prime is 21, and then effective depth is 425, and the rest of the parameter geometric properties are here. H is 500 and base is 300. It is reinforced with 332 millimeter bars. So how do we summarize the solution for this one using your flexural equation? It would be into 3 steps. We compute for K, we compute for J, and then we use your flexural equation in SRRB. For moment in terms of compression in the concrete, 1/2 fact Justin Bieber d squared. And then for moment on your steel under tension, so ASFS JD. So to do that, step number 1, solve for K. It would turn out your K would be equal to the square root of 2n rho plus quantity n rho squared minus n rho. N would be equal to 200,000. It's not specified its normal weight or what, so we assume it's normal weight. Therefore, we use EC equal to 4,700, the square root of 21. Therefore, N would be 9.29. We turn to, or we use a whole number or the nearest whole number equal to 9.0. Also, to compute for rho, it's AS over DD. There are 3 reinforcements, so 3 multiplied by single area would result to 768 pi square millimeters. Rho now would be equal to the area of steel over BD. In here, your BD would be 300 and the effective depth is 425. We store the value 0.01892 and we use the exact value later on. So it will be stored on A of the calculator. If you're following through, later on you just call out your values in computing other parameters. For K, using the equation here, so it would result to a value of 0.438. Again, we use exact values later. After step 1 solving for k, we transition to step 2, which we solve for j. Using the exact value for k, j would be 0.854. Again, we store that in the calculator. Step 3, we use simply the flexural equation under your concrete and under your steel. So one is 1/2 FCK dj d squared, and the other one is ASFS JD. Putting the values here, we remember that FC is actually equal to 0.45 FC prime, and then K is here, J is here, B is 300, and D is 425 squared. Computing for that would turn out that it's 95.71 megapascal. For the other, AS is 768 pi, FS is given 170 from the given problem. Your J is 0.854, but we use exact value to come up with better results, or with exact results. And then D is 425. The value would be equal to 148.89 megapascal. In problem number 2, we are asked the moment capacity. So we have two options, either to adopt 95.71 or 148.89. The final answer would be maximum, and moment capacity would be 95.71 megapascal. It should be, the maximum should be the least of the two values. For sample problem 3, this is taken from a board exam type of question. So a reinforced concrete beam having a width of 300 and an effective depth of 520 is reinforced for tension only with 528 millimeter bars. Given that Fs is equal to 128 megapascals, Fc prime equal to 27, Fc equal to 0.45 of Fc prime, and N equal to 9, determine the following using WST. For number 1, the balance moment capacity of the beam. For number 2, if the tension steel is 528 millimeter bars, determine the moment capacity of the beam. So it's been taken here that the solution would be to solve for K, for J, and then for flexural equation in SRRB, either using under concrete and the other one is coming from your steel. However, because number 1, we are specified to use moment capacity or balance moment capacity, so we will be using this. Compute for K, but in particular, it should be K balance, given as 1 over 1 plus Fs over NFC. J balance would be produced from your K balance, and then we improve your equation under compression equal to 1/2 FCKBJD BD squared. Alright? After doing so, we'll repeat the same process, but this time we'll just compute for K and J, because number 2 is not balanced condition anymore. So going for number 1, let's resolve. Solving for K, your K balance would be this, 1 over 1 plus Fs over NFC. N has been given to be 9, Fs is 128, and Fc is equal to 0.45 of Fc prime. Therefore, we can compute K to be 0.46071. So I hope you're trying to compute. You can pause the video if you want, and then compute first for K balance to check whether this is correct or or if you can get the correct answer, similar to mine. For step number 2, solving for J, this is 1 minus KB over 3. So again, pause the video if you want to, and then compute for JB. JB would be equal to 0.84643. We store that, so either you start storing KB at A, and then JB at B. Lastly, we use the last value, our last step, which is using flexural equation in SRRB. So either it has in concrete 1/2 fucked Justin Bieber D squared under balance condition. This would be the working equation. Pause the video if you want, so you can check if you can compute for your moment capacity. So the moment capacity would be given as 192.17 kilonewton meter. Now, using your equation for moment in steel equal to ASFSJD, so what we have would be this equation equal to 174.45 kilonewton meter. So the moment capacity would be equal to 174.45 kilonewton as our final answer. For 3.2, we solve for K, but this time we don't use K balance, but we use K equal to the square root of 2n rho plus n rho quantity squared minus n rho. Your rho would be equal to AS over BD, so you can check the value, pause the video, and see if you'll have the correct one. Rho would be 0.01974, and we store that in our calculators. Knowing that n is equal to 9, we can solve directly for K, applying the equation above, and so K would be 0.44430. Store that again. Next step is to compute for J. Pause the video and check if you can compute J correctly. J would be 0.85190. The last step is to use your Flexural Equation in SRRB under Working Stress Design Principle, in which moment is equal to 1/2 FCK JBD squared, and moment could also be equal to ASFS JD. In terms of concrete, use exact values. See if you can get the correct answer for the moment capacity. 1/2 0.45 times 27, which is your FC, multiplied by 0.44430, your K, multiplied by J times BD squared. This is your M in terms of concrete. Next, in terms of steel, using exact values for J and K, we'll have M is equal to ASFSJD. Remember that AS are 5 areas of 28mm bars, and then FS is 128 from the given. Your J is to be stored at 0.85190 value, and then your D is 520. Multiplying them all together will result for M equal to 174.57. So under a normal condition, K, your moment capacity would be 173.54. It's just less, it's greater actually by at least by not more than 1.2 kilonewton meter from 3.1. So what if we don't want to use the steps? We don't want to solve for K, solve for J, and then use Flexural Equation. But we want to apply the concept and our understanding of our cracked sections when we're computing concepts and bending elastic stresses or elastic bending stresses. So ang gusto nating mangyari, we could have an alternate solution. From the figure, it has 300 millimeters at the base, and then it's reinforced by 528mm bars, and the effective depth is given to be 520. In here, because this is a crack section, your concrete will remain at the top and it will hang your steel at the bottom, converting the area equal to NAS. Now, I simplified this already. Your 532 28 diameter bars multiplied by 9 is equal to 8820 pi. And then label this now as C equal to KD, and this remaining will be 520 minus C. Step 1 could be taking the moment at the neutral axis of the transformed section. So in order to do that, or to because when we do that, we can actually compute for C. So this is the area of the concrete by its lever arm equal to the area of shear steel by its lever arm. So C can be computed by this equation. Area of concrete 300 C, lever arm C over 2. Area of steel 8820 pi, lever arm 520 minus C. So please compute for C, pause the video, and try if you could come up with the exact value equal to 231.038 millimeters. Again, that is from the extreme compression fiber distance to neutral axis. Knowing C is equal to 231.038 and establishing a while ago that multiplying D with the investigation factor K would result to C, we can solve now for K and J. C is equal to KD. Therefore, if D is equal to 520, K would turn out to be 0.44430, similar to the value a while ago. But here, there is less memorization of formula. Only what we did is compute for the height of your C, and then compute for K, and now compute for J. J is easy to remember. It's just 1 minus K over 3. So J would be, this is just an error. It should have been J, not J balance, okay? 0.85190. Then, we can now apply your flexural equation in SRRB, wherein it is 1/2 FCKJBD squared for concrete and ASFSJD for your steel. Your moments would turn out to have the same values as 3.1 or 3.2 using the conventional steps 1 to 3. But this is an alternate solution, so you can apply that in everything, on every analysis here for it. So this is very good because this applies concepts and understanding of what is the investigation, and then the design or analysis, or the analysis of your crack sections. So in terms of steel, it would still turn out to be 174.57. Therefore, the final answer is that the moment capacity is equal to 174.57. So I hope that you understand this sample problems, and using the latest formula under working stress design principle, SRRB, and the criteria and guidelines for the analysis. Next topic would be design of SRRB. That will be discussed on my next video. Thank you and bye-bye.